Hi everyone, so today we're going to talk about infrared spectroscopy. I'm going to focus on the principle or the theory behind this infrared, or in short IR spectroscopy. IR spectroscopy can be used to study or to characterize organic molecule, organic compound. In a molecule, they are atoms. Atoms and atoms, they are connected with one another through bonds. So the bonds, they are actually not rigid. They are vibrating. They are vibrating at rest. And for the bonds which are with dipole moment, for the bond which are with dipole moment, which is resulting from the difference in terms of electronegativity between the bonded atoms. So for example, if you have a CH or CO, CO bond, they are with a difference in terms of electronegativity, so the bonds is with dipole moment. For this kind of bond, the bond that with dipole moment, it can interact with IR radiation. So different bonds, they are vibrating at different frequency, so they interact with IR radiation with different frequency. Before that, let's look at what is this vibration. So vibration, we can divide vibration or classify vibration into two modes. One is stretching, one is bending. In stretching and bending, the atoms or the changes, the atoms, they are connected through bonds. In stretching, the changes occur along the line. So the bond is now stretching, become longer and shorter, longer and shorter. This involves changes in bond length. For bending, when the bond is bending, it means that the atoms, they are moving up or down, in front or to the back. So they are with different modes of, there are actually many different modes of bending, and this motion, this moving motion does not occur along the line of the bonds, and this involves change in terms of bond angle. So maybe let me draw in this way, it's easier for you to understand. When the atoms move up and down, or to the front, to the back, this will involve change in terms of bond angle. So different types of bonds, they are actually stretching or bending at different characteristic frequency. For example, OH bond, C double bond, O bond. They are different bonds, they are vibrating at different frequency. They are with dipole moment. So when this IR radiation, when we supply IR radiation to the molecule with different types of bonds, and the bonds, they are vibrating at different frequency, the bonds, the vibrating bonds will absorb IR. The vibrating bonds will absorb IR, which is with exactly the same frequency, with its vibration. And this will cause us to see, on the IR spectrum, to see different absorption bands. We'll be able to see different absorption bands. These are the absorption bands on IR spectrum. And this allows us to use IR spectroscopy to study or to characterize an organic compound. So in the IR spectrum, the x-axis is wave number. It is with unit cm-1. So as you can see in this example, you can see a lot of absorption bands. Okay, you can see absorption bands. They appear at different position on IR spectrum. They are with different wave number. And for the y-axis, it is percentage of transmittance. Okay, the line, the up and down of the line indicate how much of the radiation that transmitted through the sample. So maybe let me show you the instrumentation in the IR spectrophotometer. In IR spectrophotometer, we have the sample compartment, the sample, which is the organic compound. Okay, and we have IR radiation supply. The IR radiation supply that we use here, or the mostly used range of IR radiation that we use for the study of organic compound is 4000 to around 400 cm-1. Okay, so as you can see here, the way that we label the x-axis is different, like what you have learned in mathematics. Okay, the way that we label IR spectrum. 4000 on the left, the big number on the left, and the small number on the right. Okay, we can set the instrument to supply or to screen the sample with 4000 to 400 cm-1 radiation. Okay, radiation, IR radiation with this range of wave number will pass through the sample, and the sample, the compound, it is with a different bonding. They are vibrating at different frequency, so they absorb radiation with different frequency. Okay, so after the absorption, so we have absorption here. Okay, absorption happen here, and the non-absorbed radiation will pass through or transmitted. Okay, will be transmitted, pass through the sample to reach the detector. And the detector is connected to computer. The computer will convert the data into readable IR spectrum. Okay, like what you can see here. So the absorption is caused by the vibrating bonds. There are different types of bonds, so the absorption happens at different position. Okay, at different position on IR spectrum. And the transmittance, okay, they may be low transmittance or high absorption, or medium absorption, or weak absorption. So in the next video, I'm going to share with you about different factors that affect the position of absorption bands on IR spectrum, and the factors that affect the intensity of the absorption bands. That's all for today. Thank you.